Ah, there we go. I thought I was unmuted before. Apparently I was not. I was just asking people to give me just a minute to get PyCharm started, and then we'll get going. There we go. In the lecture. So, Project One. We're going to spend some more time on this in just a minute. I want to talk about that. It's due a week from tonight for our section. Yes, I know it's due this Friday night for the major sections. Don't worry about them. The earlier you can finish it, the best, but you do have until next Monday night, so don't worry about it. We've got a lot of time. However, as I mentioned last week, we want to get started early on this and get ahead of the game. If it's the first major program you've written, if you're an experienced coder, you know how much you can do, you're fine. But if it's the first major program you've written, you don't want to get caught up, Sunday night, wondering why the heck this error message won't go away. I mentioned last Wednesday, I went through how to get the file in the assignment from Professor Hamilton's public directory on GL. I told you that by today, you should have at least been able to get that file, get it to wherever you're going to work on the program assignment, either on your laptop in PyCharm if you're going to do the code there, or in your directory on GL if you're going to do the code there, or whatever, and make sure it runs. I showed you last week how to run it without an error, so that's not a problem. I mean, it doesn't do anything, obviously, but it works without causing an error. And hopefully, I didn't tell you had to do this last Wednesday, but hopefully you've at least been able to write the code for the function that prompts the user for the two player names and reads them in. That's something that's fairly straightforward. If you've done more than that, that's great. If you haven't done that yet, you really need to get working on it. In addition to the lab stuff tomorrow, both Kevin and Mariah are going to spend as much time as you want talking about Project One. So tomorrow in lab is a great opportunity to get questions answered, get more information, get whatever help you need. So if you prep for it, get what you can do tonight, get your questions lined up. Tomorrow in lab will be a great time. They'll be available. A reminder, and one of the reasons for getting Project One done is Test 2 is Wednesday of next week. That's the 14th, according to my calendar. Later this week, probably Thursday, Friday, I will put a sample exam out on Blackboard again. The test is Blackboard, just like last time, and you can expect about the same number and type of questions. You can expect about 10 multiple choice, true, false. You can expect about 5 short answer, explain something, or write a couple of lines of code, and you can expect 2 programming questions. Now, the test is cumulative because it pretty much has to be, right? We can't let you forget about integers and strings and variable declarations and constants. It wouldn't make sense to pretend you didn't know that. It will emphasize the things we've covered since the first test. So it will include recursion, which is both today and Wednesday's lecture topic. It will include 2D lists. It will include string slices and list slices. It will include all of that material. By the way, I apologize for not having gotten today's lecture notes up on GitHub ahead of time. I just got caught up in a couple of things. So I'll get them up right after lecture today, along with the code samples. But at any rate, so for the test, as I said, you can expect it next Wednesday to be about the same as last time. 10 multiple choice, true, false, 5 short answer, 2 program. I'll get a sample exam up later this week. Today is recursion. Wednesday is more recursion and more talk about the program and some other things, wrapping up. Next Monday, the 12th, will be a review. I'll talk about the sample exam. I'll talk about anything I discover I've missed. I'll talk about whatever else. And then Wednesday, the 14th, will be the exam. Then Monday, the 19th, we will jump into the last part of the semester. And the last part of the semester, starting that Monday, the 19th, is where we're really going to diverge from the major sections. That's where we're really going to be start different. with no criticism of the major sections, they are focusing on learning computer science topics because these are building blocks that they're going to need when they're juniors and seniors. We try to make it relevant to you in your major and something that you can use in what you're doing as majors in engineering or music or whatever, or business or finance or whatever. So in the last third of the class, we kind of diverge and we get into a lot of graphics and we get a lot of tools and we get a lot of libraries and we get some stuff that actually, then leads into Comp Sci 291, the second semester Python class. So that's what's ahead. For now, let's talk about Project One some more. Okay. Now, I went through it last Wednesday, so hopefully you've got it, you're familiar, you know what's going on. One of the key things to think about is how do you want to represent the game board? Let me change the slide of this, lay the layout. How do you want to manage the game board? Well, if you think about it, right, you have a total of 14 cups. 2 of the cups are Mankalas. The other 12 are the top and the bottom that have stones, and you move stones around. So if you think about this, you represent the cups as a list which will hold integer values, and the integer values are the number of stones in that cup at any time. Okay, and remember that, let's just say we call it cups is a list. And then maybe, when we lay out the board, the Mankalas are cups sub 0, and it starts with 0 stones, and cups sub 7, and it starts with 0 stones. Okay, and that means you start with Mancala, the Mancala. Now, bear in mind right now, if you try to do this, if you try to go straight from this statement to this straight statement, that's not valid Python. I'm illustrating. I'm not giving you code solutions. But this is basically what you're going to do. You're going to have to figure out a way. If you want to do this, this is fine. But you're going to have to figure out a way to start from an empty list and get to these values. And then you just need to make sure that cups 1 through 6 boy, I can't type today. And cups 8 through cups 13 all equal 4. Right, because of course there's 48 game pieces, there's 48 stones, and we start out within those 12 cups 4 stones per cup. So if you want to do something like this, and again, I'm giving you pseudocode, not actual code, because you do have to write this, but it's not hard to think about it. When you think about the structure, this is actually not hard at all to write. You should be able to write all this easily. That will be a data structure, and it lets you manage the game board. Now, to handle a move, the player's input is called choice. Okay, let's say I have a variable called choice, and that's the player's input. So I have a statement, something along the lines of choice equal int, because I have to convert the string to an integer, of input, please enter your move. Okay, now you have to validate this. I'm not going to validate it, but again, that's fairly straightforward. I'm just going to ask the user, and now the user enters a choice. So I'm going to start at cups You know, I'm going to start at cups, whatever, 4, 9, doesn't matter. So here's the deal. How many stones do you have to move? The number of stones you have to move is the number of stones in cups of choice. So we're going to comment. Number of stones to move is the value of cups of choice, right? That's how many stones you have to move. The first one, you pick a cup, there are 4 stones. You have to move 4 stones, okay? So we can do it with a for loop. We can do it with a while loop. But I'll do something like for I in range of cups of choice. Okay, that's how many stones there are. And I have to add 1 stone to each of that many cups. I say something like cups sub choice plus I plus equals 1. That adds 1 stone to each cup. And don't forget, when you're done, out of the for loop, after everything's done, you have to now set cups of choice to 0, okay? Because we moved all the stones out. The warning here is that if you set this to 0 first, this for loop's not going to work, right? If you do this first, this for loop's not going to work, so you have to do this first. That is not plus 1, by the way. Sorry for that typo. That is plus I. Okay. It adds 1 stone to each cup necessary. Okay, and then you set it to 0. So this is the core of a move. So what you need to be thinking about in writing Project 1 is how you want to manage the game board. In one way, you don't have to do this. If you've done it another way, that's fine. Don't let me distract you from the way you're going. You think of the game board as just a list of integers, 0 through 13, and each element in the list has the number of stones in that cup. Now, when I say you have to validate input, remember when you ask the user to enter a choice in this statement, right? The user cannot enter cup 0 because that's a Mancala and you can't take stones out of Mancala. The user cannot enter 7 because that's a Mancala and you cannot take a stone out of a Mancala. And the user cannot enter anything less than 0 or bigger than 12, or bigger than 13. Sorry, 0 through 13. Okay, the user cannot enter 0, 7, anything less than 0, or anything bigger than 13. So when I say right here that I'm giving you a little bit of pseudocode, but I'm not validating input, what you have to do to validate the input is make sure that the user gave you something 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. That's what you have to show. If the user didn't give you 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, then you have to reject it. You have to give the user a polite error message instead of, sorry, that's not valid. Please try again. So you have to validate that input. For simplicity in going through this lecture material, I just said, okay, let's assume they did and it worked. Again, here's the guts of a loop that would let you move 1 stone into each cup. You just add 1 to the number that's there. And then cups of choice equals 0 because you've taken them all out. But remember the order here, if you set this to 0 and then run this loop, you're going to have a problem because, of course, the loop's never going to execute. The loop's going to be false right off the bat. So that's a little bit more on Project 1. So again, you should, by now, have downloaded that file from Professor Hamilton's public directory on GL. You should have gotten that file where you want to work on this, PyCharm on your laptop or on GL itself. Some people actually do all their coding work on GL, and that's great. You should have made sure that the program will run without an error. It doesn't do anything again, but it runs without an error. You should at least make sure that you can, prompt the user for the 2 names and the names of the 2 players and read them in. And you should start, writing the more significant code that actually executes the game. This is how you run a turn. You've still got to figure out how to call the function that draws the game board and things like that. That's simply a matter of putting things together. Now, what you're going to have to do, and I may talk about this Wednesday depending on how people are doing, but if you have your cups as a list of integers 0 through 13 with the various number of stones in it, if you look at how you draw the game board, you're going to have to do just a little bit of conversion. You're going to have to come up with a slightly different argument to call to match the parameters. It's not hard. It's fairly straightforward. You're just going to have to think about it for about 2 minutes and you'll get it. Okay. So by Wednesday, I want to make sure everybody's most of the way there. If you have any questions when you go to lab tomorrow, ask Kevin, ask Mariah. They're keyed up. They're ready to help. They know this is good stuff for them. By Wednesday, and we'll cover this as well, we'll talk about Project One some more in class on Wednesday. You should be really making progress. If Wednesday comes and you're still way behind on the program and you're not even sure you know how to prompt for a username, we might have an issue. So let's talk about that then. But everybody should be way ahead, should be way ahead of that by Wednesday. I understand you're taking other classes. I understand you've got conflicts. I understand you may have younger siblings who are out on spring break who you want to see if they're in high school, etc. I get it. But let's be working on this. Let's not wait till Sunday night and go, wait a minute, where do I copy that file from to begin with? Let's get this done, folks. All right. With that, I want to start talking about recursion tonight and Wednesday. I acknowledge up front, recursion is always a difficult topic for me to lecture on because I have a hard time understanding its application anywhere other. Excuse me, my allergies are murdering me. That was a bad sneeze. I apologize. Anyway, I have a hard time understanding recursion in the physical world. It is an incredibly important topic in computer programming. It's a major foundation of computer science. It's really, really important to learn it and understand it. But I have a hard time understanding it as a practical thing in the physical world. So I'm going to do the best I can. What we have learned so far is called iterative programming. Okay, even if there's a loop is an iteration, a for loop and a while loop, those are iterative codes. Sometimes a problem is really easy to solve if you look at it what's called recursively. Now, recursion in computer science occurs when a function calls itself. Okay, when a function calls itself, that's called recursion, or more generically recursive programming, but we go with recursion. As I said, it's an incredibly useful tool, but it can be difficult to grasp for just a second. So let's go on. Now, here is a statement up front, just like I did with for loops and while loops. If you can solve the programming problem with recursion, by definition, it is a fact that you could use iteration. You could use functions, you could use while loops, you could use for loops, you could solve it iteratively if you could do it recursively. Recursion means you could have done it iteratively. The other is not true. You cannot, not everything can be solved recursively. So why use it? Sometimes it just makes the problem easier to solve. Let's go to PyCharm. Let me get a new file here. Yeah, I hate it when PyCharm does that to me. And let's call it April 5th coding.py. And let's take the problem of calculating some number factorial. The factorial of some number. First, we're going to do iteratively. And we've talked about this. We use this as an example of while loops and for loops and what have you. Okay. So if we want to solve, we'll get a number equals int of input, enter a positive integer. And we will calculate the factorial. Product, let's call it factorial. Fact equals 1 for I in range 2 to number. Fact times equals I. Print number factorial is fact. Okay. Let's see if I made any mistakes or if this is going to run. Enter a positive integer and we will calculate the factorial. We all know by now that 5 factorial is 120. And I messed up somewhere. Oh, I messed up here because I can't stop at number. I have to go to number plus 1. Let's try that again. Five. There we go. And undo that. Now, what this does, if you look at it, put a comment on it, this calculates 1 times 2 times 3 times 4 times 5. Okay, and this does it iteratively. Every time it goes through the loop, it adds 1 to the index, the iterator, and it goes through and it multiplies. So this is called an iterative solution. Now we're going to do this as a recursive solution. Okay, so I'm going to define it as a function. Recursive fact. It's going to take as a parameter a number. Now, I'm going to write the code, hope it works, and then I'm going to explain it. Okay, so just follow with me. If number is less than or equal to 1, I'm going to return 1. Else, return recursive fact of number minus 1. That's my function. That's my recursive solution. Okay. And then down here, I'm going to call, I'll do the if name num equals int input enter a positive integer, and we will calculate its factorial recursively. answer equal recursive fact of num. Print the recursive answer is answer. Okay. So now let me come up here. Well, I'll just run it. It'll work twice. Hang on. Okay, this is the iterative version again. Now, this is our recursive code. Enter a positive integer and we'll calculate its factorial recursively. 5. Okay. Oh, that's because I can't type. There is a typo right here. And we'll try this again. Let's try this again, see if we can type again. No, we can't. Here is my error. How about that? It actually works. Okay, let's talk about this function here and explain this code right here and what we're doing. Okay. To solve a problem recursively requires a simple case that you can answer recursively. Now, it is a mathematical definition, and you can go into all the math you want to explain why. I'm going to skip that part. But 0 factorial is 1 by definition. 1 factorial is the product of all numbers up to and including 1, which is 1. So if number is 0 or number is 1, by definition, the answer is the factorial is 1. 1 factorial is 1. Now, the way I wrote this, if you asked me for -2 factorial, I'm going to tell you -2 factorial is 1, just because factorials of negative numbers get bizarre and you have to establish rules. In many math lectures, factorials of negative numbers are not defined. In lots of other classes, they are, but you do weird things. I'm just going to tell you, if you enter -2, you're going to get 1 for an answer. From a computer science standpoint, this is what we call the base case. And when we go back to the slides, that's going to be important. The base case. The base case is a solution, is a problem whose solution is so simple, I can just straightforward do it. What is 1 factorial? 1. What's 0 factorial? 1. We're done. Okay. We also then, since we care about more than trivial cases, we have other things that are complex enough that we can't just answer them off the top of our head. Yes, 2 factorial is pretty easy, but stay with me here. You know, if I asked you 6 factorial, you might get 720, but I asked you 10 factorial off the top of your head, you probably don't know. You might, but probably don't. So that is what we call the recursive case. Now, if you want to program recursively, then you always have to have 2 things. A base case. This is a part of the problem that is so easy to solve, we could do it straight away. 1. And a recursive case. It's a version of the problem that we can't answer straight away, but we can simplify. What this does, if you execute this code, we're going to put in some print statements here after the else. We're going to say print number is number. And we're going to run that. I'm going to go back up and comment out this iterative solution, just so I don't have to keep doing that. Okay. Now I only get the recursive solution. Okay, let's see how this works. Give me 5. Notice that now it said number was 5. The argument num in the main program was 5. In the function, number was 5. And so this code right here, if number is less than or equal to 1, well, number was 5. It's not less than or equal to 1. We came down here. That's why we printed out this statement. And now we said return 5 times, call this function recursively with number minus 1, which is 4. So now this function calls itself recursively. And remember when we started talking about functions in Python a few weeks ago, we said you could pretty much call a function from anywhere in a program. And I said at the time, yeah, you can call a function from itself. That's called recursion. Well, here we are, ladies and gentlemen. We are at the function calling itself. The function calls itself number minus 1. Remember, number was 5. Number minus 1 is 4. So now we entered this function, number is 4. Now 4 is still not less than or equal to 1. So we came down here and we had the print statement, print number is number. And sure enough, we printed number is 4. The next thing we did is we called the recursive fact again with 4 minus 1. 4 minus 1 is 3. Okay, so 4 minus 1 is 3. Number is now 3. Is 3 less than or equal to 1? No, of course it's not less than or equal to 1. So we can't do this. We have to come down here, and then we said print number is, and lo and behold, we printed number is 3. Now we called recursive fact again. This time, number minus 1 is 2. 2 is not less than 1. Sure enough, we printed number is 2. Then we called number minus 1. Well, 2 minus 1 is 1. Now, we called recursive fact number is 1. Is number less than or equal to 1? Yes, it is. Return 1. Where do we return? We do not return necessarily to the main program. We actually might. If you asked me in the main program for the factorial of 1, we'd return to the main program. We return to wherever called us. Okay, we return to wherever called us. Well, where called this function with recursive fact of 1? The answer is who called us with recursive fact was this function. It called itself. So now we have to return to itself. And now I'm going to go back to the slides and do the best I can to explain to you what is happening here. But that is an example of recursive programming to do something simple you already know how to do iteratively. Remember, I said if recursion works, iteration would clearly work. Here's how you do factorial iteratively. We did the same recursively, but this is just a good illustration. Okay, let's go back to the slides. For recursion, you have to have a task that is simple enough that you can do by yourself. It's the base case. If it's too hard to do directly, you do part of the task and get somebody else to help you with the rest of it. And this is called the recursive case. Couple of things to notice. And I'm going to give an example, and I understand it's kind of a lame, hyped up example, but bear with me. The point to pay attention to is this recursive thing only works if you do part of the task yourself. If you delegate everything to your friends and don't do anything, recursion is not going to work. Just like anything else, your friends are not going to help you if you don't do anything. You expect them to do it all. The other part of this is when you get to your friends to help you, you have to get your friends to help you do a simpler version of the task than you had. If you ask your friends to do the same incredibly difficult task that you had, well, the odds are, but they may not be able to do it any better by themselves than you did. You have to give them a simpler task. So you have to do part of the task yourself. and get other people to do the simpler version. And if you don't, you're in an infinite loop. Okay, and to illustrate that, go back to PyCharm. When we called recursive fact, we gave it a simpler version of the problem. We said calculate the factorial of a smaller number. This is what we mean by giving it a simple version of the task. Make it easier to understand. I have to calculate 100 factorial. That's hard. I'll do part of it, but can you please calculate 99 factorial, because that's easier. Okay, so that's what I mean. If I give you the same problem I had and I don't make it any easier, it's not going to work. This will not work. If this was recursive factive number, we'd be in an infinite loop. So your base case has to be something that you can and will do by yourself, and then you have to ask your friends for a simpler problem. Here is my hokey example. I am at my house in Ellicott City. My new UMBC computer is in. I'm about 10 miles from UMBC if you look at a map. My car's not working. Okay, my daughter borrowed it, and that's the last we're going to say that. I don't want to walk 10 miles to UMBC and walk 10 miles back. I just don't. So that problem by itself is too hard for me to solve. But you know what? I might be able to solve this recursively. Now, I mean, there is an iterative solution, right? I can get off my lazy butt. I mean, I could call Uber or something, but we're going to ignore that. I said it's a hokey example. An iterative solution is for me to get up and walk to UMBC. Walk the first mile, walk the second mile, walk the third mile, walk all 10 miles, get my new computer from the department, and walk back all 10 miles. It works. I get my laptop. There is an iterative solution, but it's a lot of work. I don't want to walk 10 miles. The recursive version is, you know what? I know people. I got people. I'm willing to walk 1 mile each way. So what I'm going to do is I'm going to walk from my house 1 mile down to this friend's place on that's just off Route 40. And I'm going to ask my friend Steve, hey, Steve, you owe me a favor. Can you go the other 9 miles to UMBC and get my laptop? Look, I gave you a simpler version of the problem. You don't got to walk all 10 miles like I would have from my house. I did part of the work. I walked 1 mile. All I'm asking you to do is walk 9. Steve grumbles and he says, what the heck? I'll do it. Well, Steve walks a mile and then he runs into Becky and he says, hey, Becky, can you go get Arsenal's laptop at UMBC? It's only 8 miles, right? I walked a mile. Steve walked a mile. Now we're only 8 miles from campus. You owe me a favor. Becky grumbles and she takes off. After a mile, she comes to the next person. Tom. Tom owes me a favor. And so what we're doing, I said it's a hokey example. I have a hard time coming up with one in the real world that works. But what's happening is somebody, if I get 10 people, Tyler, my daughter's boyfriend, only lives a mile from the campus at UMBC. He lives off Bloomsbury, right? So Tyler's going to walk the last mile over to campus and pick up my computer, and he's going to walk back the 1 mile to his apartment, and then everybody's going to bring it back. Okay, so at the end of the day, I have my computer. And what happened? I walked 1 mile to Steve's house and 1 mile back. I only had to walk 2 miles, not 20, not 10 miles each way. Steve walked 1 mile to Becky's place and 1 mile back. He only had to walk 2, not 20. And so on. Tyler only had to walk 2 miles. He lives close to campus, not a big deal. Okay. Nobody had to run or walk. I pretend we can run 20 miles round trip. Everybody did 2 miles, and I got my computer. That is the best physical example I could come up with of a recursive problem. Okay. All it takes is 9 friends who either like me well enough or owe me a big enough favor that they're willing to do this. And we can get it done. But if I can get it done, great. Nobody had to run 20 miles, 10 miles each way. And I got my laptop. Life is good. The base case, right? The guy who could do the problem was my daughter's boyfriend, Tyler, who lives about a mile from campus. Okay. Tyler agreed that walking 1 mile from his apartment on Bloomsbury to campus and 1 mile back with my laptop was really not too hard. And so Tyler just did it. That was the base case. I think it says she because when I was originally sketching it out, I said my daughter, but I'm going to pick out her boyfriend. So he's going to do it. Tyler's going to do it, right? That's the base case. You live 1 mile from the UMBC campus. Can you walk over there and get a computer and bring it back? That is a problem that is simple enough that I know how to solve. Okay? That is the base case. This is a straightforward, simple problem. I know how to solve it. I can do it. Good. Everybody else, me, Tom, Steve, Becky, and so on, was part of the recursive case. Each one of us made the problem a little simpler. My problem was I was 10 miles away. I made it a little simpler by walking 1. And so, Steve was only 9 away. Steve made it a little simpler by walking 1. Becky was only 8 away, and so on. Every person made the problem a little simpler, got closer to the laptop, and then eventually we got it done. If each of us, if we don't make it simpler, if Tyler comes over to my house and I ask him to walk 10 miles each way, guess what? He's probably going to tell me no. Right? Because he's my daughter's boyfriend, not me. So we had to make the problem a little simpler. We had to make the problem simple enough so that, he was willing to do it. Like I said, he's a nice guy. He'll do me a favor, but there's a limit to the favor he's going to do me. Again, it seems like fake. You got to have friends who are willing to do that. You got to have friends who, by amazing coincidence, live in the right place. It's hokey. But in a computer science standpoint, in a programming standpoint, those friends we're calling on are just copies of functions, right? They're just copies of the same functions. They're clones. They're copies of you. Okay? They're clones with different parameters. And the U is just the software function that can clone copies. Now it's not a hokey example. Now I don't have to have friends, Steve, Becky, Tom, who owe me favors or like me, and they happen to be 1 mile closer to the place. Okay? That's something that is real and useful and meaningful. Okay, here's the code for factorial. What I want to do is cut down to, if I can find it, hang on, the illustration of how this works. Okay, here's an example I give. We'll watch I'll explain a short video. And it's the same illustration of what happened. I don't want Python 3.6. That's the latest I can get. Gee whiz. This is just an illustration of what happens. Okay, and the nice thing about this is you can execute 1 line at a time. If you look at the red arrow, that tells you the line of code that Python is the next to be executed. Okay, so let's step through this. And you can see we're going to talk about what stack frames are in a minute. But this tells you that you started out with the main program running, and it knew about a function called recursive fact. Okay. This line ran here. Okay, let me go back. This was the first line that executes, right? Because the main program is always where you start. So we're at the main program. We have what's called a stack frame. And this is really more Wednesday's lecture, but I want to introduce it to you because this is important to how a computer works. The computer keeps a stack that represents where you are in the program. And it's got this global frame that says when the main program's running, this is where I am and this is what I know about. I'm in the main program. Up here are all my other stuff. I know about something called recursive fact, which is a function. which is what's illustrated up there, sorry. What's illustrated up there is a function called recursive fact. I know about it. I can refer to it. Now, the next line of code. Well, the first line of code to be executed is number 9. Okay, and so we're going to get asked to input a positive integer. I'm going to keep this small. I have to enter my integer. And let's just make it 3 because otherwise this is going to take the rest of the class period and I don't want to. Okay. Now, notice we have called, or we're getting ready to call, recursive factorial and our argument. This will be on the test next week. In the main program, this is called an argument num. It has the value of 3. Okay. And now we jump up to the function, and now we're going to execute in the function recursive fact. This is highlighted in dark blue to indicate that we are no longer in the main program. We are now in recursive factorial. We are in this function, and the parameter number takes the value 3 because that was the argument. The argument num was 3. The parameter number is 3. So we are now here. Okay. The next statement executed is the if. Is 3 less than or equal to 1? Well, obviously, you know what happens. So we jump down here, and we're going to print number is 3. Okay. And this up here at the top of the screen is the output you're going to see. The number is 3, right? That got executed. Now, the next statement we're going to execute is this return number times recursive fact, etc. Our recursive case. Now, keep an eye on these stack frames. I'll explain what they are fully in a minute when we walk through this. But frames help the system, help Python and Windows or Linux or Mac OS remember where you are in the program right now. When we were in the global frame, we were in the main program, and we knew about recursive fact as a function that we could call. Then we knew that the variable num was 3 because that's what I typed in. Then this frame ended. Now we created another frame, and that tells the system we are now executing recursive fact, and number was 3 because that was passed as the parameter. Now, since we just executed line 6, the return, we created another frame on the stack, and number is 2. 3 minus 1 is 2. Okay? So what's going to happen now is when I go next, we're going to start executing recursive fact with number equal 2. Okay, so we start executing. 2 is not less than or equal to 1. So we jump down here. The next thing we're going to execute is the print statement. So we print number is 2. The next thing we're going to execute is this return. When I execute line 6 again, what's going to happen is we're going to create another frame on the stack. The function is going to run again. Lo and behold, there is another frame on the stack, and this time number is 1. Okay, now I'm in this recursive fact function, and number equals 1. What's going to happen is when I execute line 2, if number is less than or equal to 1, that's going to be true, right? Because number is 1, which is less than or equal to 1. It is going to be true. We are now in our base case. We are going to return 1. That part is easy. The key to pay attention to here is where do we return to? When we return 1, we do not necessarily return to the main program. Up until today, anytime a function returned, it returned to the main program or wherever function called it. Helper functions get called by other functions and they return to that function. The reason this stack is important here on this left side is that tells you where you're going to return. That tells you where the program is going to return after it finishes execute. When I click next, we're going to return the value of 1. This this frame, this recursive fact with number 1 will now terminate. This is going to go away, and we are going to return specifically to this function. So the stack frame tells me where I return, and when this function ends, I'm going to return to this function, right? So let's do that. The next statement is if number is less than or equal to 1, which it is, I return 1. Okay. And now, notice the return value is 1. And I'm going to go back to this function. Now, I return to this function. Where was I in this function when I called? So when this function called itself recursively, it was right here. So you return control to right here. The returned value was 1. Number is 2. Number times the returned value is 2, right? And so now this function is going to end with return value 2. This function, this part of the stack frame, is going to return 2. Okay. Similarly, when it returned to recursive fact right here where number was 3. The return value it got was 2. 3 times 2 is 6. So this statement is going to execute, and I am going to return 6. Now, because this is the last one of the recursive calls, I am going to return to the main program. When I return to the main program and execute line 10 right here, recursive fact of 3, the value of that calculated by that function is 6. So ans is now 6, and when I print the recursive answer is 6. So I don't know if that helped or not. It helps some people. I mean, some people learn visually, other people don't. For those of you, us really, because I'm one of the ones like that, who learn visually, hopefully that explained some things about this. And the link will be in the slides when I post it if you want to do that yourself with other stuff. Okay. What's happening is that you can go through and call these frames. So that's what I meant with return. There's another thing. I got 20 minutes. What else have I got in this slide? Okay. I want to skip that other illustration of tracing Fibonacci. We'll get to that in a minute. Okay. Python, what do I mean by a stack frame and a stack of frames? A frame is a list, an environment, a list, an element, a block, whatever you want to put it, of everything that the computer knows right now. So in that example, when we started the main program, what the computer knew was I'm in the main program, and because I've seen the definition of this function, I know that there is this function. That's all the computer knows. And so when it is in the main program and starts executing, its frame is, I'm in the main program, I know what this function is, all right, give me code. Then when it called the function, it said, I am no longer in the main program, I am now in this function, and I execute the functions. In that frame, for the function, it knew what its parameter was, right? It got passed the value as a parameter, so it knew what that was. That was really all it knew when it started. Now, the stack of frames controls what instruction gets executed next. In that illustration that I walked through, where I showed you the recursive factorial, it highlighted with the green arrow, this is the statement I'm executing right now, and with the red arrow, this is the statement I'm executing next. Now that shows the sequential versus iterative versus recursive versus whatever, right? Because that says I'm right here right now, but next I'm going to be here. So Python and all languages, all computers, Windows, Linux, Mac, whatever, you have to know what instruction gets executed next. You have to know where to go, okay? And so how Python keeps track of it is with this stack of frames. This is going to be an explanation of something I said before. What variables are in scope and can be accessed? Now, I talked about this in functions a little bit. A variable in scope is a variable that Python knows about right now. I know what this variable is. I know what this function is. I know what its value is. I can look at it in the symbol table. I can't access anything else right now. Okay. And where to return. Where do I return when this function finishes? Okay. That's what a stack does. A stack of frames does. It helps you keep track of what instruction gets executed next by the computer, what variables are in scope and can be accessed, and where am I going to go when this function finishes. Now, I say the term stack. Stack is a computer science term for a particular data structure. And what happens is only certain things are legal on a stack. You could put something on top, on the end of the stack, or you can take something off the top. You can't yank something out of the middle, okay? The classic illustration is the cafeteria. You've got a stack of plates on the cart, okay? If you go into the cart and there's a stack of plates in the cafeteria and you need a plate for your meal, the only thing you can do is take a plate off the top. Or if you're washing the plates, you can put new ones on top. That's it. You cannot yank out the plate 10 deep in the stack. I mean, if you tried to, you'd probably break a lot of stuff and the cafeteria workers would not be happy with you. All you can do is put things on top or take things off the top. That's it. So in computer science, we conceptually do the same thing. If it is a data structure called a stack, the only thing we can do is add to the top or take off the top. That's it. You will sometimes hear the term LIFO, L-I-F-O. L-I-F-O is pronounced LIFO. It stands for last in, first out. So the way computers work in general, and the way Python specifically works, is it manages its functions as a LIFO stack, last in, first out. The most recent function to start has to be the next one that ends. Other functions can't end until we're done here. When you put this all together, and I am going to work through that same example again and illustrate these concepts. And we'll also do this on Wednesday because I always set aside 2 days for recursion. When we take this data structure called a stack and the rules for frames, and we take into account frames, and the frames say this is what instruction is next, this is what variables I know about, this is where I'm going when this is done, this is what determines how a Python program will work, okay? All of this determines how and why your Python program works the way it does. That's the definition of the language, okay? And because it's a stack, remember, only the top of the stack can be executed. When you look at that green arrow on that graphic, the only thing being executed right now is something in the top frame, okay? This is what I just said. You can get the most recently added item. It's a way of organizing data. There's actually a link to an illustration, again, for people like me who learn visually. And I admit, I learn things visually. Okay. More definition, a frame is the set of all symbols, everything in the symbol table, all the variables, all the constants, all the function names, currently known to Python. The first thing you do when you start the program is you push the main program's frame onto the stack. When the main program finishes, when that last frame comes off the stack, we're done. That's it. Ain't no more functions. When the functions ends, you pop the frame off. Okay. Let me go back to the factorial again and try to give you a better, let's see if I can still do this. Okay, here we go. Try to give you a better illustration. So now, the program is going to start. At this instant right now, I haven't started the program. There is no current statement. There's nothing. When the program starts, the main program frame is going to be pushed onto the stack, and we're going to start executing. So let's get started. Okay? Haven't done anything yet. Haven't executed. There's nothing on the stack. Here we go. We got to the main program. The first thing Python does when you get to the main program is it pushes a frame on the stack, and it says, I am the global frame. I am the main program. This is where we are executing right now. What do I know about? What is in scope? What do I know about? I know that there is a function called recursive fact. It's over there. I can call it when I need it. That is the only thing I know. I know that the next instruction is going to be down here. Okay? And now I execute the statement, and it says I need to input a value. That's down here. When I input this value, 3, Python now knows that num equals 3. Python knows that num equals 3 because that's what I typed in, and it executed this statement. So now the only thing Python knows is that there is a recursive fact function over there somewhere, and I know that I have an integer variable called 3. This is in effect the symbol table. This blue highlighted thing that's on the frame is in effect the symbol table for this frame. It's what I know about right now. It's what's in scope when I say that. Okay, let's go. Now I called a function. What do I do when I call a function? When I call a function, I push another frame onto the stack. Now, I apologize. I looked for a visualization thing that doesn't go down like this. Just bear with me. The top of the stack is going to grow down. The top of the stack is always where the blue thing is. I put this on top. I am now in recursive fact. Okay, I am now in recursive fact. I know that I had a parameter, which is an integer called number, and I know the value of number is 3. So I now know that I can start executing, and this is what I've got. Now, in terms of scope, remember that things declared in the main program are called global variables, and they can always be accessed from functions, but you shouldn't. Just because you can doesn't mean you should. So from recursive fact, I can address number. I can also address num in the global frame because that's a global variable. I don't want to. I'm not going to. In this frame, in this function, I only know this. Now I'm going to go through a little bit quicker because you've already seen the code. I do my if statement. I do my print. And I now call another function. I call recursive fact again with number equals 2. When I call recursive fact again, what does Python do? Python creates another frame. Python puts that frame on the stack. Python says, I know that I have a variable called number. That was a parameter that got the value 2. I know that I am in this function here. The next line of code to be executed is up here. Let's go. Now I can execute. Is 2 less or equal to 1? No. I'm going to print. It's hard to see up in my top right corner, but there actually is, the printing is actually happening. You saw that last time, but the code is actually executing. The printing is happening. And now I'm going to call recursive fact with number equal 1. Python says, aha, I'm going to push the term to add another stack to the top, another frame to the top of the stack is push. Python says I'm going to push another frame for this function called recursive fact. That's where I'm executing. Now I'm going to execute with number less or equal to 1, and now I'm going to return 1. Well, remember what we said about functions. The instant you execute a return, the function is over. That's it. No second chances, no leftovers, nothing to pick up the pieces. We're done. Okay, so therefore, we're going to execute this return 1, and then the function is gone. Now, keep an eye on this blue box that says recursive fact with number 1. Okay, it's now gone. Nothing up my sleeve. It disappeared. We're now back in recursive fact with number 2. What happened? When that first recursive fact frame was finished, when I did the return, the instant you execute that return, that frame was popped off the stack. It was gone. Now, where does control return when you pop a frame off the stack? When you pop a frame off, it goes to the next thing down in the stack because the only thing you can do is go to the top. You can't go anywhere else. So now I am executing recursive fact with number equal 2. Now I've got to finish executing that because I'm in this return statement. And again, watch what happens to this function right here. That frame's gone. That function ended. That return statement got executed. That frame was popped off the stack. Now I'm in the original call. That frame's now gone. That frame is now gone, and I am now back in the main program. And in the main program, I know that recursive fact is still a function. I could call it again. If I wanted to write more code, I could call that function again. I know that num is 3, and I know that ants equals 6. Okay. Now notice from the main program, I cannot get to number right here. Why can the main program not access number? The answer is because when the main program is in charge, when the main program is on the top of the stack, there are no functions running. All the function frames are gone. Number doesn't exist. It is unknown. So therefore, the main program cannot access a variable defined in a function because it's not in the proper stack frame. That function is gone. It is not in scope. So when we say the main program cannot access a variable in the function, what we mean is, since there's nothing here on the stack, the main program, the global frame, there's no number here. If you say something in the main program about number, it's going to give you an error. It doesn't know what number is. It knows I've got a function. It knows I've got num. It knows I've got ants. That's all it knows. So the things, the variables in the function are out of scope for the main program, and you cannot access them. Now, as I said, when I showed the function, because this global frame existed on the stack at the time, you could actually reach back from the function to the main program and get that global variable. but you really shouldn't. The global variable was on the stack, it was known, but you really shouldn't be doing it. Okay, now we finish up the main program, we have the print statement, and the program is done. They don't actually show this global frame stack coming off, but when it does come off, the program's done and we're set. And I think, given that I have 11 after 5 now, I'm not going to try to do the other examples I have in tonight's lecture. I'm going to wait for them on Wednesday and talk in more detail about specific examples of recursive code. When the function ends, these are the things I've said. When does it all end? When the main program's code has been executed. The last few slides are other examples of recursive programming, which we will definitely cover on Wednesday to try to give you more examples and a better understanding, because recursion really is important in programming. And with that, even though my clock says it's only 5:12, I am going to declare the end of class, and I will talk to you all Wednesday. And I have a few minutes if anybody has questions, but I am going to stop recording so that I don't record your questions on the lecture notes that get posted to YouTube.